So everyone, thank you so much for joining. Welcome to part 2 of the 3-part webinar series, Building Microservices with Pulsar. My name is Karen. I'm part of the growth team here at StreamNative, and I'm so excited to get to introduce the hosts of today's sessions with you. First, please join me in giving a warm welcome to Apache Pulsar committer, StreamNative developer advocate, and author of Apache Pulsar in Action, David Karamgard. Also joining David today, we have StreamNative solutions engineer and Apache Pulsar contributor, Yannis Polizos. We are recording today's session, as you may have heard. Please feel free at any moment to put any questions that you might have into the chat, as we should have time at the end of the session for Q&A, and we do have folks that are monitoring the chat currently. With that said, let me go ahead and pass sharing over to David, and let's dive straight into part 2, Stateful Microservices.
Thank you for that wonderful introduction. Thank you so much, Karen, for that. I'm going to go ahead and put this in presenter mode really quick. So this, again, as Karen mentioned, this is part 2 of Apache of the webinar series, Developing Microservices with Apache Pulsar. For those of you who attended part 1 or did not miss part 1, just to recover what we covered there was an introduction to Pulsar, some of the terminology we used, and a basic discussion of Pulsar Functions, some of the benefits of using Pulsar Functions and the programming model that it provides for you. Then we discussed a little bit about microservices themselves, some of the goals and characteristics of that architectural style, what you're trying to achieve with the migration to microservices, about breaking a monolithic application into smaller, more manageable pieces as well. And then introduce why Apache Pulsar Functions, the serverless lightweight computing framework built on top of Apache Pulsar explicitly for Apache Pulsar, is a good fit for developing microservices. And then we got into a little bit of event-based microservices design using schema definition. And finally, Yannis showed us how to develop and deploy microservices using Apache Pulsar Functions. Now, this part today is going to pick up where that one left off, and we're going to focus more on stateful event processing and how state can be used inside of event-based systems, and when you would want to use that as part of your microservices to provide functionality required for your application. We'll also talk about the different types of state that are available and some of the different access patterns that are available for interacting with stateful systems inside of our Pulsar functions and microservices that use, need stateful information. We'll talk a little bit about the Pulsar Statestore, what's provided natively internally to users of Pulsar functions, and then hand it over to Yannis again for some development and deployment use case and walk through a scenario of using a stateful microservice. So today's agenda, we're going to focus on stateless versus stateful microservices and what the differences are and when you might want to use one versus the other. Again, focusing on some stateful use cases and cases where you need to have stateful services. We'll look at internal versus external state, the differences between them, some of the design concerns about those and when you want to interact with those, and concerns about how to interact with those, and some patterns on how to do so. Next, we'll focus on how Pulsar handles state internally, how it manages the ability to store state between function calls. And then again, as I mentioned, we'll develop a stateful microservice, deploy it, and monitor it as well, and continue to build on the example we just showed in part 1 of the webinar. So hopefully at the end of this webinar, you're able to know the differences between stateful and stateless microservices, some of the different types of state and the access patterns we're going to introduce, how Pulsar handles that, and hands-on deployment practice on how to implement and deploy the stateful microservices. So let's begin on the role of state and what state is. And again, we've been talking about this a lot. So let's talk about the differences between stateful and stateless processing and how they're both used. So stateless application is when you receive a request and apply some kind of processing logic directly to that application, and it does not require any context or previous state of the world from the existence of previous messages in order to do its work. Each message that arrives to a stateless application is completely self-contained and has all the information necessary for your microservice to act upon it in order to perform its work. So again, if you have, for example, an e-commerce site, or we mentioned the food order service, each food order that comes in is completely self-contained. It has the customer who's ordering it, the delivery address where it needs to be delivered, the list of items, the menu items that the customer has requested as well. And so all that information is completely self-contained. We don't need to know about the previous orders that came in order to be able to act on that. Now you compare that with a stateful application in which you receive a request, or stateful microservice. When you receive a request, in order to do your logic, you need to have some previous context or an idea of where the state of the world is at any given point in time. And the quintessential example would be something like if you're computing an aggregate value or such as an average or summation or things of that nature over different events. So again, take the e-commerce or food order example. If you're trying to process and calculate the total number of orders placed, or the total value of all the orders placed in the last 5 minutes, you would be required to have access to each one of those individual messages. And when the next message came in, you'd be able to add that value to your previous rolling count and continue on with that. So I see somebody raised their hand. Is there a question? Nope. Okay, it's false hand raise. So let's look at this graphically. The difference between a stateless service and the events coming in, and then you're applying the logic and what's coming out at the end. So let's say you have a stateless function where you're trying to filter out events where the values are greater than a certain threshold, right? So you're looking at events coming in, and you're looking for values here who's only interested in values of X that are less than 100. So as you can see on the left, lots of events can come in. In this particular case, the third event there on the left that has the value of X of 104 does not get emitted out because it does not meet the threshold that we're looking for as far as of interest to us. But the key takeaway from this is that the ability for that function to make that determination is based entirely on data contained within those events themselves, within those messages themselves. And there's no need to process all those information. They don't need to be processed in a certain order. We don't need to retain information about the ones we've seen in the past in order to make that determination. Each one, again, is completely stateless. And this type of processing leads itself very well for high scalability, sort of work queue use cases, where you can have a high number of producers all acting on those events because they don't need to be aware of the data. There's no data delivery guarantees or grouping of the data required in order to be able to perform your function. Now, conversely, a stateful service taking the same data set would again be something where you're trying to calculate the average of a rolling window, or smoothing out those values of those events. So again, we're getting events in with the values of X, but in this case, we're trying to calculate an average at any given point in time. And so obviously it's critical that all those values have come in and get processed in the right order, and you can give a snapshot. You cannot accurately calculate that value of 86.25 without having seen all of those events. And at any given point in time when the next event comes in, you have to add it to that value, add a count of the events, and then you can obviously produce a new average value based on those inputs coming in. The key being here that this function is required to see all of these events and retain that information about the previous events in that state of that event somewhere else in an external system, either internally or externally to the Pulsar function framework itself, in order to produce that correct and accurate result. So let's look at the differences between internal and external state and how we define those within Pulsar. So we define external state as anything where your state, the data that you're persisting from your Pulsar function is going to reside in some kind of external data store that's outside of the Pulsar application itself, the Pulsar framework itself. So things like databases, key value stores, caches, in-memory data grids, things of that nature, anything that stands outside of Pulsar. Conversely, internal state is when the state resides inside Pulsar itself, either inside a Pulsar topic or through a state store, the Pulsar Statestore, which is kept inside a bookkeeper internally. The difference being between these two that you don't need to connect or interact with a third-party system. So there's much more resiliency internally when you have that information available. It's native to Pulsar itself. You don't have to interact or have credentials to interact with these other systems, and there's some latency benefits as well. But that's the key for purposes of this discussion, what we consider external state versus internal state. So looking at state and how to process it, right? For external state, it's really a matter of initializing a connection with the external system and then interacting it through its normal querying API, for example. So all of them are going to follow a similar pattern of establishing a connection to a third-party system through some sort of endpoint, most likely providing some set of credentials, security credentials, and then keeping that connection open through multiple calls, and being able to intelligently make calls to that system, whether you're doing a key value store, you're doing a GET lookup, or if you're doing a database query, you're querying it by a specific SQL statement or that sort of thing. So the considerations when working with external systems, you have to be concerned about and pay attention to external system latency, right? Every time you have to make a native call, when your function is making a call to external system, there's an inherent latency with that each call that you make. There's also some network latency involved in system availability as well. Now your application and your microservices are wholly dependent on an external system outside of your completely outside of your control, outside of your system. And you have to build in some resiliency into your systems and be able to handle situations where you can fail gracefully in the event of lack of availability to those systems. So that's something you have to consider when you're dealing with those systems. Conversely, internal state, things become a little more complicated because the data resides and may result in a different Pulsar topic, and there's a pattern or technique for actively reading that information and bringing it inside to a Pulsar function. There's also the Pulsar Statestore, again, which I mentioned. While it does support the key value lookup semantic, it is not designed for high throughput writes and reads. It's more of a more higher latency, low usage sort of use case. So even though it implements the key value pattern, you do not want to heavily use that as you would a traditional network cache as well. And so some of the common use cases for internal state are like topic lookups for data enrichment, stream correlation from different topic IDs, or access to previous events to apply some sort of algorithm. So again, if you have a shared use case, you're trying to do a stateless processing, but you need to get access from the previous events that came in the system that exists inside a Pulsar topic, that's sort of a case where you have to go back and get this sort of thing. And so some of the considerations about when you start writing applications that are going to use internal state is you have to make sure that, again, you have to have a copy of that state and keep it inside of memory. Or if you're going to go read it from a topic every single time, there's going to be latency from that. You have to consider things like keeping your state fresh and evicting, older events and making sure that you have the most recent copy of the data. So data consistency, data availability, sort of concerns when you're trying to replicate that you've now brought internally to your system. And then there's also the read-write speed. Again, if you're going to be reading from multiple topics or trying to join things in or going back and forth to Apache Bookkeeper, Statestore, there's some latency costs associated with that as well. So you need to be aware of that and make sure that your system can accommodate for that. So we can revisit the use case we were looking at the last time from webinar part 1, where we have a food order delivery service, right? So you have a fictional food order delivery service. You're sitting at home, you want to order some food, and these food orders are coming in. So the mobile application, as people are going on their web, on their phone, adding some items to their cart, saying, okay, I want to add a hamburger and fries and shake, and I want to get that information sent. And then it will produce what's called a food order event. And so this information might have some user ID, might provide us passwords or some other sort of credentials so that we can do fraud identification, make sure it's the right person, provide maybe contact information, and then have some details around the order itself, what items he wants, when he wants it delivered, what's the delivery address as well. And all that information gets published to a food orders topic. Right now, the first thing we may want to do in order to do some validation is do a user info lookup function, right? And so that information about the user itself, again, like we're doing validation, let's say on his password and user ID. That information is going to be stored in an external data store, most likely a database. And so we need to go access that information in order to, maybe enrich data and output it to the enriched food topic orders there on the left. So we're going to do some sort of enrichment with that. So the code for that's going to look something like this. Again, for those of you who missed part 1 or just to review, the Pulsar function looks something like this. It implements the function interface, and on the left-hand side is a food order object. That's a schema definition type, a JSON schema that's defined what that message looks like, and returns a type void, which means does not produce any output topics. And every time a new message is published to that food order topic, a food order object is delivered, and that process method there at the top, there with the override annotation is invoked. Right. And so the first step we do is this is sort of a common pattern where you first check for initialization, because we're going to have to go and interact with a Postgres database in this case. Right. So we do an initialization block and we do it one time. And now if you look at the implementation of that init method down there at the bottom, you can see that we're passing the context object from the Pulsar Functions SDK. And it allows the user to pass us secret values and user-defined configuration values there at the bottom, including things like the database connection URL. We can get that value along with the database username. Again, we can do get secret, so that data can be encrypted and stored so it's not exposed sensitively, but we still need that information, and a database password as well. And then we can get all those values from the user provided and configured function itself, and then initialize the Pulsar lookup server or the Postgres lookup service and use it inside our Pulsar function for the remaining for all additional invocations. So it's a one-time cost. Once it's done, we set the flag that that's been done to true. And so all subsequent calls don't have to go through this logic. But once we've gone through the process of initializing a client to the external system, now we can simply, use that information to do the querying. So in this case, we're going to take the user email off of that food order object because that's a primary key we can look up in the database. And then we can make that call to that database service and retrieve additional information, right? And once we have that information back, we can take that, we can output a new object there, to the enriched or to the enriched food order object by adding some additional information that we pulled off from the user info we retrieved from the database. And so this is a common pattern. Again, we use Postgres for this scenario, but that's true for all different systems. That you basically have to create an initial connection, and you can have some error checking logic as well if something fails, but it's the basic pattern. And again, any sort of system that you have in this case, a Java, since you have a Java programming language, any sort of Java client too, you can access using this pattern as well very easily. Now let's switch gears and look at how we access internal state in a common use case for an update stream as well. So again, let's look at trying to get this user info from an internal topic instead. So rather than going to a database, let's say that we have some user info, that same information we need, but now it's stored inside a different separate topic. And again, so we're getting a food order coming in that same topic. We have the user info lookup function. We need to do some lookup in order to enrich that data. But this time we're going to get that information from a different Pulsar topic. So how are we going to go about doing that same task and doing it internally? So the code is slightly more complex. This is a very common pattern that you want to use the reader interface inside of Pulsar that's available to you, but it follows a very similar pattern at the beginning. So again, you have the process method that's invoked when the new food order comes in, and we have a one-time gate to check if our state is loaded. So we're going to constantly load state, doing initializing of the readers, loading the state as well. And then once we have that information state in place, we can process it, right? So let's quickly jump to the init readers here, right? So I see we have a question. Is there a question in here? Oh, okay, sorry. Right, okay, so again, the init readers is the first thing. So again, Pulsar has a reader interface, and that's what we're specifying here. So we're creating a brand new reader and telling it of the type user info that we're going to retrieve. And then we have to take the user info and we're specifying a user provided topic. So we have to know the topic name that we want to read from. And then we start from in this case, we're specifying, we started all the earliest message in that topic itself. And we're going to read that information again using a read compacted, which is true, which basically skips duplicate keys and only returns the most recent value of that key. So again, this user topic could have, it's going to have information from multiple different users, maybe do multiple entries for the same user. The compacted annotation basically tells us to skip over, only read the most recent record for any particular key or message or individual user. And that's what that sort of makes sure that we don't have that information or duplicates. So we're sort of doing some deduping on our side. And then we start, the state loop. We continuously have a background thread running in the background here. On the right-hand side of the screen, you can see that we sort of have that info reader that we've initialized and set up to run to start reading the messages, right? And pulling them in, one by one, and deserializing the user ID, getting those bytes again, which is the key value, and then taking that information, that user information, and storing it inside an internal cache, so that when we need to do lookups on that cache, we can just go back and say users cache.get and look up that user ID key. And then that way we don't have to go to a database. So now we've cached that information locally, and that reader is always continuously running. So as new events get published to that user info topic, for example, we're going to get updated information in our cache. And so the most recent data version of that data will be available internally. And so this is a common pattern for accessing state that's stored inside a Pulsar topic from inside a Pulsar function. And again, Pulsar functions can be used as a microservice. And so this is another pattern for implementing that and accessing that data. Let's see if this moves next. So let's revisit the use case that we left off with the food order. So once we've done a validated food order and rich food order, we introduced a pattern last time. The very first microservices was this validate food order use case, right? So a food order is coming in and it has 3 different pieces of data. Again, it has payment information, it has a delivery address of where the food is to be delivered, and it has some different food items that the customer wants to deliver. Now, in order to validate that that order can be delivered and fulfilled, we have to check on 3 things, and we do it in parallel for efficiency, right? So the first one is a payment service. So we split out the payment information from that topic and invoke a payment service like a credit card validation, or if we're doing Apple Pay or PayPal or something like that, we need to go and make sure those funds are available. We have valid credentials, and those funds are, we have a reserve on those funds, and we're able to get that information, get that payment for that food. Otherwise, we're just going to stop right there. Similarly, for the delivery address, we go through a geoencoder because we need to enrich the data to get a lat long address or lat long coordinates for a specific address, because we're going to route our drivers using lat long coordinates on that. And if for some reason they've given an invalid address and we can't map back to that, we'll be alerted to that at this point in time, or we'll be alerted that it's outside of our service area, for example. And so we can also notify the customer if there's a bad, maybe they put in a bad address, for example. And then the third, we have to go to all the different restaurants and sort of solicit and make sure the ones that are open, right? So though you're asking for a certain food item, it may be past the time that those particular restaurants that can provide it to you are open, or make sure that those items might be out of stock, or might be discontinued, things of that nature, because not every restaurant may have the same hours of operation or menu items or availability of stock. So we have to confirm that there's a restaurant somewhere that can honor that order and have it ready for a driver to pick up as well. Now, if all 3 of those things pass, then we can we aggregate them back together. So again, they're running in parallel. We have to aggregate those and wait for those things to arrive one by one, and then once those are all done and completed, we can say it's a validated order and move it on to the validated orders, and let people start doing order fulfillment, actually notify the restaurant they can start making the food, things of that nature, and then eventually notify a driver when it's ready, so on and so forth. If any of these fail, we want to be able to notify back to the customer immediately, say, hey, there's a problem with your order. Maybe you put in a bad credit card number. We need you to update this as well. So, this is a good case for a Pulsar Statestore. We mentioned, the bookkeeper under the covers, right? So at the end of this module, we're going to talk a little bit about how we can store some of this information, that coordination information, about as each one of those events get done. We store that information in Pulsar Statestore to handle it internally. And then we show how to access that information inside a Pulsar function. So the use case, again, is, we have 3 different orders coming out, and we need to store that information. So under the covers, Apache Pulsar has Bookkeeper there already for storing the messages. Apache Bookkeeper also provides a table service, which provides a key value paired lookup sort of semantics as well. And that Statestore is made available to you inside the state API within the function context, that context object we saw earlier in the code, that's made available to every single function call inside that process method. So you can access that state at any given point in time. And just to simplify the interface here, this is how it's defined under the covers. You basically have, put and get semantics based on key. You also have a delete option as well, so you can start clearing up your Statestore. You don't want it to get too big. And there's both a synchronous version and an asynchronous version of those operations as well. And so it's very, very basic, simple processing semantics. Also, from a maintenance standpoint, you can also query that state as well at any given time and continuously watch it. So if you wanted to monitor this externally, make sure that everything's going on inside as well. You can also do a put state. You can do query state. You can do put state to update information. So you can look at that information as well. And this is sort of a way that you can monitor it if you're trying to troubleshoot your functions or have issues with the state, you're not sure what's around, you can sort of see these things. There's also an additional set of API within that context object that allows you to record different things for monitoring as well, things like counters, so you can count the number of orders were processed in the last hour. That's also can be stored inside the Statestore and pulled off later, and that's a special semantics around a counter. Specifically, increment is the only option you have. You can increment, and you can clear the counter. And then you can also record metrics as well. So if you're trying to record the number of, let's say, invalid login attempts, for example, that could be a special metric you want to capture outside of just performance metrics like CPU and bytes through. You can also start identifying things like, hey, we're starting to get a lot of erroneous orders coming in. You can have a monitoring on that as well. So it's another sort of way you can record state internally inside of like a microservice if you want to monitor those sort of things and make that available to a system for fraud detection, things like that. So with that, I believe this is Giannis's part of the section. So he's going to show you how to design a stateful microservice, how to handle input from multiple event streams, and how to use the Pulsar Statestore. And with that, I will stop.
Thank you, David, for all this useful information. So let me just share my screen really quick. Can you guys see my screen? I will take this as a yes. So going back to our microservice architecture, this is what we are building again. And just for a quick recap, we in the part 1 of the webinar series, we created the food order source that basically emits some records inside this food order topic that later it is consumed by the order validation topic. And then it goes ahead and in an asynchronous way, it invokes 3 different microservices: the payment service, the geoencoder service, as well as the restaurant service. And each one of these services in turn goes and queries an external API, as you can see over here. Finally, after all the invocations are completed, everything gets aggregated here on the order aggregation service. And the orders are forwarded whether they were accepted or declined from the restaurants. Also, as you remember in part 1, we have our Abro schema definition files here, where we specify the schema for each one and every one of our microservices. Here we have everything concerning the food orders. We also have the validated food orders that basically contains all the information from the restaurants, the information from the geoencoding service, as well as from the payment service. And one thing to note here, as you remember, in order to deploy your Pulsar function, you need to specify the configuration over here. We specify everything as a YAML configuration file. And after that, with this script we have provided, it's just a matter of running the Pulsar admin command with functions create, specify the input configuration file, and then you need to deploy everything. You need also to specify your jar file. So let's take a closer look to each and every one of our microservices. But before doing so, let me also run this deploy script we have here to have everything running as a Kubernetes pod, so we can also check the logs and see how our services do behave. So a quick recap on the order validation service as well. As you remember, this is the first one, our entry point for our food orders. And here we're receiving a food order, and for each order, we want to extract the order ID, the information we're going to send to the geoencoding service, as well as the information for the payment service. Then we forward everything to the appropriate topic by invoking these 3 different services. And we also send an empty validated food order. It's an empty payload along with the order ID, so we can let the aggregation service know that a new order is in place, and we are waiting for the response from these 3 different other services to be aggregated together. So inside here, we have created some simple services. We have, for example, the first one is the geoencoding service that, as we saw, accepts an address and then basically creates an HTTP call to some external service. And for demonstration purpose here, we're just modeling the HTTP call. But we also provide some code using the Google geoencoding API. Over here, we just over here, we are setting the necessary information for our service. And after that, we just create a new validated food order record and add the necessary information for the geoencoding and just forward it forward to the order aggregation topic. And the same logic again applies to these 2 other services here. We have the payment service that accepts a payment. It goes and checks the type of the payment. By default, we set the validation as false, and we wait for the service to validate our payment. And based on the type of the payment, we invoke a different service in each case. Again, this is some mock HTTP calls that just return through here. And again, if the payment was successful, we say that it's authorized, and we create a new validated food order record along with the payment information. And again, everything is sent forward to the aggregation topic. And lastly, we have the restaurant service that for each food order it receives, it extracts the necessary information from the payload. It queries an external mock service for the restaurants and provides an ETA along with some other metadata for the food order, whether the restaurant accepted it and other information. And again, everything gets forwarded to the order aggregation topic. And one thing I want to mention here, and I think it's an excellent reference. So if you, even though we're making some mock HTTP calls here, in real world scenarios, as David mentioned in the beginning, you might want to think about how your external system behaves. For example, we might have an external database or a third-party API that at the point we're making the external HTTP call, it might not be available, or we might have some network issue. And for that reason, there is an excellent library. Let me just grab my browser over here, which is called Resiliency for J. And it is for implementing a lot of resiliency patterns in Java. So for example, you might want to introduce something like secret breakers or retry patterns. I mean, in this case here, since you're communicating with an external API, you might want to handle retries. And in case, for example, your third-party API is unavailable, introduce something like exponential backoff and try with some delay inside. And along with that, let me also open it. Last time, we also saw David's book, which you can download for free. And inside here, in this section, I mean, okay, for some reason, it seems like I have some internet issues. There is this chapter for resiliency patterns, which I encourage you to go through. It uses the same library over here, the Resiliency for J, and it implements all kinds of different resiliency patterns. So it's an excellent reference if you want to see how to implement it using Pulsar Functions. And I know that a lot of you are also using Python for implementing Pulsar Functions. There is this library I used back in the days. It's called Tenacity, which handles retries and with exponential backoff and all these kind of things. But for other things like secret breakers, I'm not familiar with some libraries in the Python ecosystem. So moving forward, at this point, let us also check our logs, for example, for the payment service to see what the payload might look like. And let me just check the logs for a service. And so right here, as you can see, we received some payments from which we extract the payment method. In this scenario, we have the credit card. And after we query the external API, we just sent to the aggregation topic a new validated order that only contains the information regarding the payment. And so moving forward to our last microservice here, it's this order aggregation service where we need to aggregate using some kind of state all the messages that have been handled from the different microservices. So for each validated food order we receive, we need to extract the order ID first, and then we need to query our state here. And again, as we saw on the slides, it's a matter of just accessing through the context object. And again, everything is returned as bytes here. So we are querying it using the order ID. And if the state is empty, we just initializing the state because it means we are still waiting and for the other service to complete. But if our state is still present, we retrieve our state and deserialize it from the internal Statestore. And we just update the fields based, for example, whether it was some information sent from the payment service, from the G encoding service, or the restaurant service. We're checking if the aggregation is complete over here. And if the aggregation was completed, we are routing to the appropriate topic. We also delete the state. If it wasn't completed, it's just a matter of just realizing the state again and putting it back in the Statestore. And on the routing here, we also making sure that the payment was authorized and the order was also accepted from the restaurant. And so this is getting forwarded to the accepted orders topic. Otherwise, we are providing the reason why it was declined, and we are forwarding everything to the declined orders topic. And let's see how everything looks like inside our pods. But first, I have also provided some simple consumers here for both the accepted orders topic and the declined orders topic. And the code is pretty much straightforward, where first we need to initialize a Pulsar client. Over here, we'll also use some kind of authentication method. And then it's a matter of just bringing up a new consumer where we specify the input topic, the consumer name, where we want our consumption to start, a subscription name for our consumer, and it's just a matter of just using some basic while loop to read the messages. So let me just start my consumers here, and at the same time, let us also take a look at the logs of the order aggregation service to see what happens exactly. So if I use the logs for my pod. So as you remember also, for the food order source over here, we are introducing a small delay for every food order. And so right here, we can see that every order should be processed in the same order we are receiving it. And so, as you can see that for every food order, when it is completed, all the information, the payload is filled up from the results from the 3D and other microservices, and we just delete the state when it's finished. And so let's take a look at the results of our consumers as well. And as you can see here, these are the accepted orders. And over here, we have declined orders that update every while now with the reason why it was declined and the payload. And so at this point, we have completed creating our order validation service. And one thing I also want to mention is that, as you can see, for this particular order validation service, it is comprised of 5 different microservices. But imagine, and also source connector, of course, but imagine having hundreds of microservices. For each one of those, you will have to go ahead and package your code, create a YAML file with all the deployment options, with all the configuration here, and just run the commands over here, like we saw in this deployment script, and try and deploy it and every one of these microservices one by one. So one thing I want to highlight in this session is a FunctionMesh, which is a really cool project recently open sourced by StreamNative. And to be honest, it starts to become one of my favorite ones. And the beauty of FunctionMesh for me is that it makes your Pulsar functions, it makes your event streaming and application level truly cloud native. And it does so by combining all your functions, your connectors, whether it's sources or sync, in this tag right here, which stands for directly cyclic graph. And so you can combine all your sources, functions, and syncs together and just deploy them as part of a mesh. And by doing so, you're also truly leveraging all of Kubernetes features like deployments and scaling your functions and sources based on your requirements and the volume of your data. So in general, it's a really new project, but I think it has bright features. So I truly encourage you to take a look at it. And so with that being said, let's also see how we can take our validation service here and deploy everything as part of a mesh. Actually, I'm not going to go through the installation process of FunctionMesh because it's quite simple. If you go here on the documentation page on the installation, it's just a matter of cloning the GitHub repository of FunctionMesh, creating a new space for FunctionMesh. And lastly, you just go ahead and run this helm install command, which is going to deploy all the resources necessary for running FunctionMesh. The installation process is quite simple. So FunctionMesh basically is a Kubernetes operator that monitors all your pods. So inside here on the deployments folder, I have provided some sample configuration files for all the different microservices and the source connector as well, because you also have the flexibility to deploy each and every one of those independently. But we're going to only focus on the mesh file here because it deploys everything for us with a single YAML file. And so as you can see here, it's just a matter of specifying a FunctionMesh CRT type, which stands for Kubernetes Custom Resource Definition. And then you group together all your sources and functions. We have all our functions here. And it's just a matter then of specifying a name, the image you want to use for your application, the class name of your source or function, and then the configuration is more or less the same as we did with the standard Pulsar function configuration. And again, there is a lot of boilerplate stuff here for creating this file, but because, as I said, more of the configurations are the same, you can use something like Helm charts to reduce this boilerplate code here. So at this point, this is how we define everything, but you might be wondering, how do we actually, when we have our Pulsar functions, how do we create these custom images here that we want to use inside our Kubernetes cluster? And so as you remember, when we create our Pulsar functions, we want to package everything and create this executable jar file over here. And the first thing you need to do, I have provided the sample Docker file here that depending on your runtime, we are using the Java runtime here. It's just a matter of inheriting from the base class. And all you need to do basically is just copy your executable jar file under this Pulsar location over here. And after that, I have also provided this build shell script. It's just a matter of building the image and pushing it to some registry you can access. Over here, I'm just using my own Docker Hub. So this is also, as you can see, what I specify here on the image name, my Docker Hub. So now for the deployment process, let me just go ahead and clean all the resources we have deployed and wait for a little while the process finishes. So yeah, with FunctionMesh, instead of having to deploy everything step by step, you just need to run this Kubernetes file. And also one thing I forgot to mention that's really important, along with the image here, you also need to specify the name of your jar so that Kubernetes can know what is the name of your jar file. And so let's take a look here. Looks like all my resources have finished. So right now it's just a matter of running git control create command and specifying this mesh file. And you can see that creates all the necessary Kubernetes resources, and with just the simple command and the YAML file, everything is deployed again as part of a mesh. So we have everything up and running. And I think at this point, this is pretty much what we had to demonstrate in terms of code for our order validation service here. And I think with this one, this concludes everything. And I think we have quite some time for questions. And I'm going to hand it back to you, David. If you guys, I don't know if you guys want to share any questions you might have or any use cases you have with Pulsar functions we can help out with, or you want to discuss anything. I hope we have provided some useful information for you today.
Excellent. Excuse me. Thank you, Giannis. This is Karen chiming back in again. I do see that there are some questions coming into the Q&A box as well. Looks like David's been answering them during this portion, but I do see one that's still outstanding. Are you able to see those?
Okay, so it's some. I think that I see one around how state is evicted or compacted after being used. So in general, how state works for Apache Pulsar, as David said, is that it uses Apache Bootkeeper underneath. So in most scenarios, you might want to think how you want to evict the state yourself, because you store things here, you store things there, and in most scenarios, it's up to the developer to decide how he or she wants to evict their state. So you just need to use the delete APIs that are provided from the context object and handle the eviction yourself. And it also depends what your use cases and what you want to use for your state. But in the Apache Bootkeeper scenario, this is what you have to do. I really want, I mean, guys, if you want, let's make it more interactive. I mean, I really encourage you all to pump up and just share your use cases or anything you might be building with Apache Pulsar. I will be really curious to see all the amazing stuff you might be building with Pulsar functions. And I also want to hear out any opinions you might have around FunctionMesh, because it's a really cool project and I really like it personally. So come on, don't be shy.
Oops, come back.
David?
Come back to that, sorry. Nope, okay, well, thank you for that, Giannis. There are no questions at this time. Let me just share some details on.
Oh, okay. Sorry, David. I think you have one. Key share subscription would be even better, I guess, with same key for topic and state. This is what I use, but I was wondering if some other mechanisms existed.
Right. So that was a follow-up to if there is a way to avoid race conditions when working with a stateful function, right? So you want to make sure that you have data consistency. You don't have newer messages coming in, including the state before other messages come in. So you have in-order processing, and basically, internally inside the code, there's obviously all your synchronization messaging techniques and constructs that you can use. You can also use the exclusive subscription type to make sure that a single consumer always gets those same messages. And in the event of a failure, right, so you can send with an exclusive subscription type, which you can specify in any Pulsar function. You're basically saying, I'm the only one getting these messages, and that when I get that message and I happen to have a failure, and I alert Pulsar that I've had a failure, it immediately gets redelivered to me. And there's no other messages get sent in between. There's no skipping of the messages, that they're guaranteed to be processed in the order that they were delivered to Pulsar. And so that's another way to sort of control that as well, so you don't have any sort of race conditions. Yeah, that was a great question. I think this point is, again, key shared subscription does that as well, because it allows you, again, it takes the benefit of, okay, I'm guaranteeing in order processing on a per key basis, but bear in mind that with a key shared subscription, that negative acknowledgement, if there's a scenario where that happens, then the message could get delivered out of order, because that strictly from the Pulsar perspective, that subscription type does not provide that level of guarantee as far as guaranteed message ordering delivery. Because it's a shared subscription, you could get them out of order. So be aware of that. If you're using that sort of subscription pattern, and you're dealing with state, and you have to make sure that the state is completely dependent upon the order of the messages, right? Okay, and so is there any higher level Pulsar API for stream joins or materializing topics like Kafka streams? Nope, that's a good segue. Yeah, he knows part 3 talks about Flink at this time. Curious about Pulsar. So no, there's nothing built into the Pulsar framework that does that. Internally, again, we leverage existing systems like Flink or Spark or things like that are well designed to handle that. We didn't want to reinvent the wheel and then put the word Pulsar in front of it and say, hey, we have Pulsar streams, when it's really, there's lots of great tools out there and great communities around it. We just feel that that's a better solution, and that's what we provide as in our offering, as a fully compatible. We focus our effort on, Flink plugins and Spark plugins and make them as efficiently as possible, because there's great communities around those. So yeah, that's a great question as well.
And we also need to mention, David, that Pulsar functions are meant to be really lightweight, so they can also be used in scenarios, for example, like edge IoT analytics and this kind of stuff. As David said, they are not meant to replace the existing stream processors.
Yep. They're meant for very, low. They're great for single transactions. They can be used for microservices, like we mentioned. So they're a great use case for things like that. There's a question about, can you wrap state updates and writing output messages in a single transaction? So you're saying, can we have Pulsar transactions across multiple functions with that, or within a single logical transaction? That is a great question. That's something we're working for right now. I don't think right now, since the transaction API was added in 2.8 of Pulsar, if that's been exposed, or we have the ability to tweak that at the function level at this point. But that's a great follow-up with that. Let me take that as a follow-up action item. I believe that'll be something in the future. Otherwise, we're going to have an external mechanism to do it, unfortunately, that you have. But again, that's within microservices. That's not really, you don't really have a lot of transactional spanning different independent services. You sort of use things like a saga pattern or things like that to do rollbacks and things of that nature. And I know their question was specific around state internally to Pulsar functions. And so on a rollback, you have to be able to trigger that back as well. And so I think there's a way to handle that. But right now, the short answer is no. There's no way to have access to that. You sort of have to be aware of a failed message and then write and roll that entire transaction back, and do that manually by knowing or making sure that at the end that you've completed the processing and only update the state at that point. Yep, great question. There's our chat coming in here as well. How is state evicted or compacted after being used? So if you're talking about Apache Bookkeeper and the Statestore itself, and so you do not, that's not done manually. That's why that delete API is sort of there. Obviously, it's an overwriting with puts, though. It overwrites if you're using the same data, multiple times. It gets put in there. But if you do not explicitly delete older items, they just sort of build up in that table store, and there's no really background process to do that. I mean, Bookkeeper's pretty scalable. I wouldn't worry about exhausting it. If you use millions and millions of keys, it would sort of still handle that quite well. But again, there's no built-in mechanism for the Pulsar Statestore. Now, if you want to do it internally, like we show, where you're having a reader and you're appending those streams as well, then you can, and you're storing it in an internal cache structure, then I would recommend using like a library that has a built-in caching mechanism or eviction policy built into it. I know a lot of them do now, so you can say, like least recently used, or, after a certain amount of time, you have this cache eviction. I know the Guava library cache has some great eviction policy configurations and things like that. So you really have to leverage an existing third-party library to handle those things if you're doing internal state management in a cache in that scenario where you're reading data from an external or a separate topic outside of your Pulsar functions primary input topic. Then that would be a way to go about achieving that. Yeah, great question. We got another question coming in. Okay. Any function states replicated in Bookkeeper like messages are? It is a shared state across instances of that function. And so it is right now, the Pulsar Statestore is fenced in on a per function basis. So it's tied to that tenant namespace and function name, and can only be accessed by functions operating with that name. But having said that, again, you can run multiple instances of the same function. And so they all have access to that as well. And then again, since it's stored in Bookkeeper, It is automatically replicated. The table store makes sure that it is available. There's 3 copies of it persisted somewhere. And so if there's any sort of bookie outage, then it's still available. There's still 2 copies somewhere, and it sort of self-heals and replicates that, because again, it uses the underlying same mechanism, the same storage pattern, and so everything is going to be resilient and durable, and you don't have to worry about losing that state unless you happen to lose all 3 bookies that is stored on and things of that nature, which is highly unlikely. Yep. Great question. All right. I think that is everything. So again, if you have any other questions, you want to follow up with us, here's my Twitter handles, here's our GitHub repos, this is our LinkedIn. We also have additional resources as well. So he mentioned, Giannis mentioned the FunctionMesh. There's some blog posts on that. There's also the GitHub source code that's available. So if you want to play around with this some more, it's based on the source code that comes from my book, which you can download. Again, StreamNative has been gracious enough to sponsor my book, and you can go to the website and download a complete copy. It's not a partial copy. It's all 12 chapters are there. And there's also some of the preliminary work, the available chapters to date on the O'Reilly book, Mastering Apache Pulsar is there. And then there's upcoming events, live events. Pulsar Summit Europe is coming up in October. Pulsar Summit Asia is coming up in November, and additional meetups as well. And then there's always the public community Slack channel, things of that nature. So lots of different resources. We're very active in the community. Lots of ways to get a hold of us, pick our brains, continue to interact with us. Just wanted to mention that we're kind of proud to mention the fact that we're listed as one of the ones to watch. And we recently had a very nice funding round. And so we're going to be here to stay. We're going to be continuing to use those funds to continue education, build out enhancements to the Pulsar function, Pulsar in general, and all the different training exercises and everything that comes with it. We're definitely going to be hearing a lot more from us. And again, thank you so much for joining.
Yes, thank you, everybody.
And all of these links that we share with you will be sent in a follow-up email along with this recording after today. So you can share it, review it later, and all these resources will be made available that I referenced earlier.
And once again, thank you all for being here with us today. Okay.
Thank you, everyone.